All right. Yes.
Okay, so good afternoon, everyone. Welcome to the this week's seminar. And our speaker today is Konstantin Klem, which has been a long-standing collaborator with IFIS from his PhD thesis and the time of his PhD and during his Ramon y Cajal contract here. And now he's one of our official research associates at IFIS. So the floor is yours.
Thanks a lot, Maxi. Great to be here again, to see you. And yeah, thanks for having me also this week for the rest of the week. Yeah, I will talk about bifurcations and multistability in adaptive vascular networks, or in fact, it should have been in a model of adaptive vascular networks, because this is not experimental work. We're just working with a bit of data that other people have gotten from laboratory mice vascular networks. And then we're taking also an existing model from the literature. So you could say we're not doing so much new here, but there, to our understanding, there are some things missing. So we are actually first going down to a very small network. We are analyzing that adaptation model on a triangular network, where the only effect that we want to see is if the blood vessels, vascular means it's about blood vessels, they actually form a triangle or not, depending on parameters. And yeah, so much for an overview. The rest I will introduce as we go along. And so what are these flow networks, biological flow networks that we want to talk about? There is, for instance, in plant leaves, well, there's a flow coming from the stem through the branches into the leaves to supply it with water and nutrients. You can already see, well, maybe you can't see because it's too small here, but one interesting aspect that network inside the leaf is not a tree. So you might guess that this supply network inside the tree is a tree, but inside the leaf it is not. So there you have some cycles which you can't see, but I can. So yeah, so that's what the whole thing will be about. Is it tree-like, or is it a cycle? Where do these cycles come from? Where do they arise in the model, etc.? Then other examples. This is the blood vessel network, or the arterial network on the retina of a mouse. No, of a rat. Sorry, a rodent, but it's a rat. Well, and here is our now kind of large-scale vascular system of us as humans or mammals. Good. And yeah, to follow along with that question, is it tree-like or is it a cycle? Let's look at one arterial network from the mouse neocortex. Okay, so you kind of open they opened the skull of these mice, and so on top of the neocortex, you have a blood vessel network that, from which in certain points, then further blood vessels go down into the actual neocortex, right? So, but that thing is on top of it, so it's pretty well accessible once you've opened the skull. And yeah, so then you can see it under the microscope, and you can locate all the blood vessels and where they where they bifurcate, and also the nodes where actually there's a something going down into the neural tissue. Yeah, the nodes are now not distinguished here, but we know which they are, which will become important later. And there's one unique node, which is the root of the whole thing, namely where from the main artery the blood comes into this system. So that's that node, right?
Is there another landmarks?
No, that's one. Yes, one victim in the lab. Yes. So there's the whole. I'm just showing one. There's the whole data set has nine of these networks, 5 mice and 4 rats.
So whenever two blood vessels, at least in this image, whenever two blood vessels cross, this also corresponds to a place where there is something going on. Right? I mean, the blue dots always, not always, but they correspond to crossing between maybe stones.
No, now I don't know if they can actually distinguish this, if it branches off, or whether just kind of you have a node of degree 4 looks like, but they're actually 2 on top of each other. That's something I don't think it's mentioned in the paper. So in principle, when there's a node of a degree at least 3, it means that it's branching off. And all these nodes of degree 1 and 2, they are the places where it doesn't branch off inside this network, but it goes down into the neocortex itself. Okay, what you can see here. Further questions? No. What you can see here is, okay, this is not a tree again, which becomes even more visible, at least a bit. When I show the tree, when I show the minimum spanning tree still in black, and then these red nodes, these red edges, they are making this to a non-tree. Okay, so I can take out all these red edges, and then it's still connected and minimally connected in the sense that now it is a tree. Now I don't have cycles anymore. And this is in some shortest version that I can have, right? Remember, this is not just somehow embedded network, but these places are actually the places on the surface that we're looking at. Good. So why then should you have cycles at all in such a network, right? The simplest solution is to reach every place that you need to supply, just build a tree, right? So I suppose that, for instance, the system of freshwater pipes in this building, well, I don't know, but I assume that this is also a tree, right? So it's just branching. There's the main pipe is coming in, and then it's branching off. But normally you don't have any cross connections. But why should you have them? Well, if you have damage, then you have, of course, more resilience from such backup connections, right? So you have multiple paths. If one fails, then you can still use the other. We'll not spend so much time with this here, but just to show another nice picture from their paper with that same data that we just had. So they were actually able to observe that. Okay, so here's a cycle in one of their observed networks, and now they can actually go in and block. Here's the original one. Here they block that blood vessel. And then they can actually measure the flux everywhere, and so under normal conditions the flux is in this direction, but when you block here, then you are actually using this blood vessel in the opposite direction in order to compensate for the damage here. Okay, so that makes sense. Just kind of backup connections having backup connections would be the reason for this cyclic structure. But then another kind of buffering occurs when you actually have load fluctuations. Okay, So for instance, again in this neocortex, what they can also measure is that if there's higher activity in a certain locus, higher neural activity, then there's also more blood flow into that locus. So kind of your neural processing actually correlates with some fluctuations in the need for a supply. So it's natural that it's not constant. And so this is what we're actually going to look at here. What happens in the model that I'm going to introduce, what happens under load fluctuations, and when are these load fluctuations so large that you actually get cyclic structures. Okay, so then now comes a bit of definitions in order to fully understand what the model is about. But mostly you can kind of think electric, because this flow network will be basically a linear resistive electric network with conductances and so on. Okay, so our network is a finite graph with n nodes, and then each edge is assigned a conductance, and that is symmetric. So things flow in our pipes, in our blood vessels, things flow as well in one direction as in the other. Good. How is that conductance actually connected to the flow? It's like in Ohm's law. So the conductance times the potential difference, and that is here the pressure difference. So just the pressure of our fluid that's flowing there. That product of the conductance with the pressure difference, that's the flow, right? So maybe normally you write R, so you write the resistance. So the current is the voltage divided by the resistance. That would be that law here. And then you have mass balance at each point. So now you want to actually solve for the flow, and then you have to fulfill these conditions. So at some points I will pump something into the network, and at other points something will come out. So that's our kind of boundary conditions. And well, that has to just be in balance with the rest of the flow, right? So if I at one node I sum over all the neighbors and make the balance of these in and outgoing flows, then that net value has to be the inflow or outflow at that node. Okay, so that's just mass conservation. So we're not accumulating mass in our network. Good, okay, it's one more time here. And then what we're going to do is that these HI, they fluctuate on a fast time scale. Okay, on a time scale faster than actually the adaptation of these Cij happen, these conductances. Good. Then I should first say how they yes. How? Yeah, probably. I mean, it has to be laminar and all that, right? I suppose, but yeah, which we assume. I mean, so that we are in this regime, because you don't want that comes actually now. You don't want to dissipate more energy than necessary, right? So, but that okay. These are just assumptions for this kind of modeling that I just believe. So, so what we're looking at is this model here by Hu and Kai. Now we are saying how do these conductances actually adapt to the need? Okay. And how do they do that? Okay, they first define an energy functional, which has two parts. One is dissipation. That's just again, think of the linear resistive network. So here you have the conductance, the inverse of the resistance, and then and here you have the voltage difference squared. That's what you would have in a normal resistor as the power, right? The power dissipated. And there's a trade-off between this term. Of course, you want to make this term small. How do you make this term small? Well, you make the conductance large. Then more flow means less pressure difference. More conductance means less pressure difference, right? If you have a really broad or a thick vessel, then not so much pressure difference will build up over it. But of course, making a large vessel has a certain cost to it, and that is this one here. That's the cost of the maintenance of the vessel, which incurs this exponent gamma here, which regulates what happens when you actually first of all, when you make the vessel thicker, and in particular, if gamma equals 1, then you have a linear cost, which means, okay, you make the conductance larger by a factor of 2, it costs you twice as much. But the assumption is that gamma is less than 1, so it's a sublinear growth of that cost with the conductance of the vessel. Okay, that's basically a bit of geometry. So if the vessel has, say, twice the diameter, and then you would say, okay, principle is the circumference of the vessel that I have to maintain, but the flow through the vessel grows superlinearly with the diameter. So these are some geometric arguments. Yes. Well, here everything is dimensionless. So, but in principle, it has if you take the units here, then it's a power. Yes. Yes. Okay, then let's not, for the moment, to avoid any further confusion, let's not call it energy. It's just a cost function. Okay. Okay. No, it doesn't have all these properties of an energy. It's just a cost function that we assume this biological system wants to minimize. No. Energy just in the sense of something that that should be minimized. So it will. So let's go further. Let's go down here. So in fact, our adaptation rule that is derived from this has this function as a Lyapunov function. Okay, so we assume that now that the adaptation of the conductances tries to minimize this. Okay, because this is postulated to be the power dissipated. This is the energy per time that I need in order to run my system. First of all, by pumping, and secondly by keeping my blood vessels in okay functioning. Okay. Good. Good. So that's not exactly a gradient, not exactly the gradient of this, but it has positive scalar product with the gradient, so it's a Lyapunov function of this one. So this is now the dynamics of our blood vessels. Okay. But you can all the time basically also just think of this here, of this sum of dissipation cost and maintenance cost of the blood vessel. Good. The crucial thing now in the model that we already see here is this exponent gamma, and as I said, by some geometric arguments in that paper by Hu and Kai, who introduced this, it's a PRL 2013. They claim that gamma equals 1/2 is the most plausible value. Okay. Which means that yes, there's clearly this sublinear growth of the maintenance cost of a blood vessel with its conductance. Okay, so if you had two small blood vessels running that were exactly parallel connecting the same 2 points, then it would be much cheaper to put them together into one large blood vessel. All right, that's the idea. Good. Yes. What's it? No. Okay. Good. Anytime. Good. Now finally, to define the model, we need these load fluctuations, right? We have here this HI, which is the net flux in or out of node I, and the load we take the load fluctuations such that at any point in time there's one node with there's one sink with a high outflow, and the others have a relatively low outflow. Okay, so there's one special sink S that has a high outflow. Outflow means that it's negative anyway, and the others have a smaller outflow. Okay, and the whole thing and how much larger it is determined by this parameter alpha. So all you need to know is that for alpha equals 0, there aren't any fluctuations. So all the nodes have the same outflow. All the sinks have the same outflow -1 over n, where n is the number, small n is the number of sinks. So those nodes where there is any outflow at all. And for alpha equals 1, that's maximum fluctuations. There's only outflow at this node S and not at any other. Okay, and in between you just have a linear superposition of the two cases. I say, okay, there's only outflow at this one node. Of course, mass balance, something should also come in. We have one special node in our network, which is kind of the input node. That's the heart side or the main artery side, right? Remember the red node on one of the first slides? That's the connection to the pump, where things are pumped in, and that thing is just fixed, of course, and it pumps the pumping comes at a constant rate. Good. So then we're done with defining the model, and now Hu and Kai, well, they run simulations on something with a kind of network which is supposed to mimic a leaf, in this case, a tree leaf, and when this alpha, the amplitude of fluctuations, when that is small, then you get this case here. So you actually get a tree network. Okay, so all the nodes, they are actually connected to the source here, but they are connected by a unique path. There are no cycles here. Even though the network that you give it in the beginning, the network of all possible connections that, well, there's actually this kind of hexagonal grid here. So there are many more possible connections, but they don't have a non-zero conductance, right? So here, for very low load fluctuations, the system evolving according to this equation that just selects this tree. Yes. Not all to all, so it's a lattice here. Yeah, you can kind of maybe it's easier here. You can kind of yeah. I think hexagonal something, right? Yeah. Good. And then when you increase the amplitude of the load fluctuations, then you get cycles here. Okay. Good. So that would somehow explain things, and we could finish here. But what Hu and Kai didn't do was to check which parameters, for instance, you would need for these first networks that we saw in order to actually exhibit these cycles, right? So what we've done here is, okay, we've somehow changed this parameter, load fluctuations, then we get cycles. But the question is, with any realistic parameters in other networks that we know from nature, so empirical networks, like the one I showed at the beginning, which parameters do you actually need? And is that in agreement with the ideas we have about our parameter values, in particular about this gamma here? Okay. Yes.
Something I don't really get from this framework is the kind of optimization that you're solving.
Mm-hmm.
My perception is that it is a global one. So you have this kind of Lyapunov function and you want to find a minimum.
Mm-hmm.
From a biological point of view, when the conductances adapt or change,
Mm-hmm.
this cannot be global, right? I mean,
No.
But somehow the adaptation rule takes into account all the information of the system.
Okay, yeah, I went over this a bit fast. So, well, in fact, it doesn't. So, because what does the adaptation of this conductance of the vessel between I and J, what does it depend on? It depends on the conductance of the vessel itself, on the pressure difference, or in fact, you can rewrite this as the flow also. So that's kind of locally measurable, kind of the things that are happening in the boundary. They depend on the flow, of course. So that can be felt by the cells in the inner surface of the blood vessel. This is the length of the blood vessel, and that's it.
Sorry.
And then, okay, and the length you can merge that with this one, and then you can rewrite it such that it is completely local. That's the point. Yes. Thanks for the question.
How you get from one to the other? Precisely. How you go from global problem, say, to the dispersion that you see local, right? It's for one edge.
Yes. Well, to go from here to there, you first write down the gradient. So this is a function that depends on all these Cij. So the gradient with respect to, or in that vector space, and then it's not exactly that. As I said, it's not the gradient. It's but it's it has positive scalar product with the gradient. So it never points in the opposite direction. So, and the reason for not taking the gradient is that there are some problems here at zero. So when the conductance is zero, then yeah, there there's some trouble there. So so you have to multiply the gradient with a factor that also depends on Cij in order to get something reasonably differentiable here at zeros. That's
the full gradient to be that several equations for each ij, right?
yeah, one you get this for each ij, for each link ij that is at all contained in your given network, you get this equation. Yes.
And you look for special.
Yes. And the point is stationarity when you have already averaged over the load fluctuations, right? So these angle brackets is averaging over all these load fluctuations, okay? Which makes it not very handy to simulate all this. So, but yes, good. So then we thought, okay, fine. You go, you have this example. It looks nice, and okay, you'll somehow have a as you turn off or as you increase the alpha, the load fluctuations, you go from here to there. But what kind of transition is this actually? Is it yeah, what's happening there are all the cyclic closures happening at the same time or one after the other and so on. So then we reduced things to the smallest non-trivial case, which is just a triangle. Okay, so now just to understand how this transition between tree and cyclic system happens. Okay, so now 3 nodes. The node number 1 is the one where the pumping takes place, so that's our influx node, and 2 and 3 are sinks, and they are arranged on an equilateral triangle, so we don't have to deal with the length of these blood vessels. They're all just one, just unity. And then due to the symmetry here, we also always assume that these 2 direct connections from source to sink, they have the same conductance. Okay, and then a tree-like solution would look like this. So only the direct connections from source to sinks are there, and this C23 is 0, and the triangular solution has a non-zero, a positive conductance also at C23. Good. And just to remind you, now we have 2 parameters, namely this cost exponent in our cost functional, and the amplitude of these load fluctuations, which are the fluctuations here at the sink, right? So at any point in time, what flows out of 2 and 3 in sum has to be the same, but it's kind of changing how much of this, what is pumped in, is actually at 2 and how much is at 3. Good. And now I'm we're doing this here. So the model has these at each node you can pump something in or pull something out, HI, and these are fluctuating. Okay, but we look at what is supposed to be stationary is the conductances when you assume that these load fluctuations are much faster than the adaptation according to this rule. Okay, so I'm averaging this. I'm keeping the conductances constant. I'm kind of, you can think of stopping the adaptation for a moment and just averaging for a while over the load fluctuations. And then when this average balances out here in this equation, so I get 0 for the time derivative of Cij, then and for all of them, then I'm in a stationary state. Right? So in reality, they would still fluctuate. The conductances would still fluctuate because the load fluctuations are not infinitely fast. They have finite scale, but they have very small fluctuations because the load fluctuations are sufficiently faster than this adaptation can take place. Good. Now I'm skipping, I think, 4 or 5 pages of equations in the published paper and just telling you what the thing is doing here as a function of gamma. Okay, let's start with gamma equals 1.0 and vary the load fluctuations. So that vary this alpha, the fluctuation amplitude. Then for low fluctuation amplitude, the tree-like solution is the only one that we observe. And then at a sufficiently large alpha, a bifurcation occurs, and that's actually a transcritical bifurcation. So this thing here actually comes out of the negative, and well, then we don't plot the corresponding values of these edges either. So it's not a solution coming out of the blue, but it's coming out of the negative, right? Good. So here's a transcritical bifurcation where this tree-like solution turns unstable and the triangular solution turns stable. Okay, good. So for gamma equals 1, we already basically have what we wanted, or what was implicitly claimed at the beginning, namely load fluctuations can induce cyclic stable stationary solutions in these networks. So just make the fluctuation amplitude large enough, then you're above the transition, which means the triangular solution where this cross connection is also conducting, that is stable, and the tree-like solution, it's still there, but it's unstable. Good. Then for gamma less than 1, so this actually holds for all, basically for all gamma between 0 and 1, but here's for gamma 0.9. We have a different kind of bifurcation. So again, tree-like solution, you make the fluctuation amplitude larger and larger. And then what happens is that you get additionally 2 triangular solutions, one stable and one unstable. So here's a saddle node bifurcation. So a pair of triangular solutions appears here, one stable, one unstable, and the green line is still solid. So you still have also the tree-like solution stable. Okay. So I think I have multistability in the title. So here it is. Okay. So you have the scenario where you have a tree-like solution still stable and the triangular solution still now also stable. This branch here, and in between the two, you have an unstable triangular solution. Okay. Good. And then there's the case of gamma greater than 1, which is not so realistic, because that would mean you kind of say you're all the time kind of saving energy by splitting up your blood vessels into smaller blood vessels, right? So it's kind of reversing this effect that normally one blood vessel should be cheaper than a lot of small ones. So that's unrealistic. So we will not consider it so much hereafter, but just for completeness, here the tree-like solution is always unstable and the triangular solution is stable. Good. Okay. Now, in the full parameter plane here for cost exponent gamma and fluctuation amplitude alpha, this triangular motif in this model now has this overview of solutions here. So in this area, you have only one solution, which is the tree-like solution. Then you go over here, you cross this line by a saddle node bifurcation. You get two additional solutions, which are these cyclic solutions, and one of them is stable and the other is unstable. But you still all the time have the tree-like solution stable also. Okay, and then on this line here, when you come up here, when you increase the fluctuation amplitude, then you get a transcritical bifurcation where the tree-like and the cyclic solution, they exchange stability. Here's just a zoom in on this point where actually this saddle node and this transcritical bifurcation where they meet. Good. That's the whole overview of this motif. And now we've felt kind of sufficiently informed to go to the actual network, so to the actual empirical network, and try out what is happening there. No, sorry. Okay, no, one more thing to actually prepare us for this case, because we haven't looked at the length of the blood vessels. Okay, so as you vary the length of that cross connection, okay, L23 down here, you just shift the critical point of this saddle node bifurcation where the cyclic solutions are created, which is also clear. So the longer the distance between the two things, the less sense it makes to actually have this kind of extra connection between the two things, which helps you to use the connection on the right side to kind of deviate some of the flow, which should actually go to the left side. So the larger the distance there, the less sense it makes to use them, and that's what's happening here. Okay. Good. And now we just tested the model on this empirical network that I showed you at the beginning. Remember it? It has quite a number of connections in excess to a tree. So it's not a tree. It has quite a number of cycles. And so what we did was first of all to test this under maximum load fluctuations, because although we haven't proved this, the idea is the larger the load fluctuations, the easier it is to get cyclic solutions, right? Because that's what we want to do. We take this network and we ask, okay, which parameters do we actually need to choose in order for all the observed blood vessels to actually have a non-zero conductance, right? Because if they don't, if the blood vessels are there in reality, but the model says, okay, you are actually not there under these conditions, then something is wrong with the model, or we have chosen the wrong set of parameters in the model. So the model should at least assign a stable, stationary solution, where all the existing blood vessels, or all the observed blood vessels actually have a non-zero conductance, because otherwise, if they have a zero conductance, then they wouldn't have been observed, right? You don't observe a link that has strength 0. So good. So now we're checking is how much are actually all the links of the network, how much are they actually there, or which of them are there. We do this under maximum load fluctuations, and we vary gamma. And then we see that as we reduce gamma, some of these already pass out, so to speak, right? I'm plotting the conductivity of these connections here, so they're kind of, you can sort of locate them in the network here with pointing to them with these dashed lines there. Okay, so for instance, the red one is the one that goes away first here. Actually, also in a saddle node bifurcation. Just I'm not drawing the unstable branch here because it's difficult to trace, right? So the saddles are typically hard to find numerically, so we didn't make this effort yet. Okay, but we know at least that the saddle node bifurcation is happening here. Okay, so you start with the full network. You make a parameter scan with gamma, and at this point here for gamma 0.66, you do not get a stable stationary solution anymore that contains this red edge here, and likewise for others. So as you decrease gamma, there you lose more and more of the edges, but the point where it starts is well above 0.5, right? So that was kind of our testing value for this parameter, because that with geometric arguments you can say that blood vessels should use gamma equals 1/2, right? But that's not what we get here. So assuming that all is correct with the model, gamma should not be 1/2, because then we can't reproduce this network structure in the model. So gamma should be larger than 1/2. We also tested this for some of the other networks in this data set. I'm not showing that here, and similar things happening there. Good. Oh yeah, sorry. So I'm actually using this synonymously. So it's the. No. Okay. That's the difference. Okay, good. Well, each link here has a certain length, right? Given by the geometry of the network. Yes.
Yeah, the equations.
Okay. Well, it's this Cij. So yes, it's always that. So yeah, good. Yes. And well, that brings me to the end. So we have analyzed these transitions between tree-like and cyclic solutions, and they occur in our 3-node network. They occur as saddle node bifurcations for gamma, for this cost exponent, gamma of less than 1, and transcritical bifurcations, gamma, yeah, actually just equal to 1. Sorry about that. And then we have tested the model on an empirical network, or actually several. And the parameter gamma equals 0.5 from the literature for claim for vascular networks is not supported here. We don't actually get a stable stationary solution that is that observed network. So gamma should actually be much closer to 1 as a conclusion from this study. And skip the outlook here. And here are some papers. Thank you very much.
Thanks, Konstantin. More questions or comments? Yes, Lucas.
So
This exponent gamma, can it be measured experimentally? Do you think?
Not that I know of. So, but
So it's a kind of allometric scaling of some sort, isn't it? This gamma.
yes,
Like the geometric
yeah,
argument tells you
that's a
0.5.
geometric argument, but I don't know if they have actually measured it. So, yeah. Okay.
More comments?
Clarification. So when you say all the time when you say the evolution or those time-dependent equations, this has to be interpreted as an evolutionary way, is it, or you interpret it as during the embryo development and the formation of the vascular system? How do you interpret this?
Yeah, it is during the lifetime of the organism. Yes.
So that equation is supposed to describe you think it describes the embryo, so the vascular, the development of the vascular system.
Yes.
Yes, not the final.
Well, the development, because there you have growth. There are some other models for the growth of these systems. That would actually first of all answer which connections you can have at all. So here's, I mean, you're starting with this network here and say, okay, that's my set of possible connections. And now the model makes this step of saying, okay, now on this network things are running, and then some of the connections can actually get
form or not.
Yeah, can or be sustained or not. So the model is just
I don't think biologically is the growth of the vascular system is like that. So
well, not the initial growth. Yeah,
not the initial growth, or whether the blood vessel branches or no branches to go to one place or to the other.
Yeah, but the plasticity would be described. I mean, in the framework of the model, the plasticity of the
that was something I did say evolutionary. The vascular system of an animal or an individual should follow these rules, in average for all the individuals or something like that. Not the growth of a single one. That's what I thought.
Okay, no, that's
how I interpreted it as you were talking, but maybe wrong.
Yeah, so I mean, what you can inherit maybe is how the system actually can fulfill. I mean, how the system can optimize. I mean, which now at a molecular level, how do you actually implement this, right? So that would be what evolves from generation to generation.
Exactly.
So but of course the network itself is not hard coded in your genes. So
exactly.
Yeah.
Thank you.
Thank you for the talk. Why do you use this vascular data for your modeling?
Basically because we had it. So and because one reason is also that it was sufficient. I mean, it was not trivially small, but also not so large that we wouldn't be able to handle it. Okay, So you see, we kind of started testing this, and numerically it's a rather involved thing to do it. And here we have a couple of hundreds of nodes, and we can kind of deal with it. So they are much larger networks also, but we would have to optimize or numerics for that. So this is just what we can handle now.
Okay, and is there another exponent related to other type of data? Do you know?
No, we haven't tried that, and we haven't seen so much actually testing out this kind of models. So which kind of just try to observe stylized facts, so to speak, trying them on real networks. So, right. So this model just says, okay, look here, when we make the load fluctuations large, then okay, then there are cycles, and cycles are also in real networks. So that then cycles may be due to sufficiently large load fluctuations, but we haven't seen any study that for instance would take this model by Hu and Kai and really try it out on a network. That's why we did it. I mean, on an empirical network. Okay.
Okay, thank you.
Okay, no more comments, questions? I do not. Thanks, Konstantin, for the talk.
Okay.